Hi, welcome back to Math 112. Tonight we are going to talk about section 6.2, which is all about the graphs of the other trigonometric functions. So the last section we talked about was actually 6.1, which was sinusoidal graphs. And we are going to look at the other graphs now. So I'm going to give you my screen. Oops. All right, let's go to my PowerPoint here. This one's not going to be as elaborate as usual for a lot of different reasons that you really don't care about. So we're talking about the graphs of the trigonometric functions, as I said, and we're going to start with tangent. Maybe. Maybe not. Let me see what I can do. Oh, this is not going to be good. There we go. Okay. Sorry, I am on my home computer and it is a little bit dicey. So this is probably going to be fairly short because I don't want to push my luck. But I want to get you the basic information. We're going to start with tangent. And we're going to remember that the tangent of an angle is defined as the ratio of the sine of that angle divided by cosine. Or if we think about this in terms of our unit circle, that is the length of the side opposite that angle, or y, divided by the length of the side adjacent to that angle, or x. Tangent is really kind of an important function that you want to be comfortable with. So work on this one. Let's take a look at the graph of the tangent, and while we're doing that, we're going to take a look at the domain. Right now, you should be thinking to yourself, oh, this is going to be interesting, because what needs to happen? What do we need to be aware of? Tangent is going to be undefined. When the cosine is equal to 0. Why? Yeah, because we can't divide by 0. So let's go out to my Desmos, which is right here. And let's just take a look at this. So I've got our unit circle. And what's going to happen is, as I let this point go around the circle, we are going to develop the tangent function. So here we go. The other thing I want you to think about is since we said that the tangent is equal to y over x, that should make you think of the slope of this line from the origin to the point. So as the slope goes up, what's going to happen? Yeah, you know that the slope of the vertical line is undefined. And look at, let's see a tangent. Oops, it just jumped, didn't it? So notice what's happening here. It's not that the tangent function is getting really big and then just running off my screen. If I scroll way out, we can see that we actually have vertical asymptotes, don't we? So we've got regions where this function is undefined, which isn't surprising because we already said that tangent is going to be undefined wherever cosine equals 0. And sure enough, that is the case because cosine equals 0 at points that we already know. And we want to make that pi over 2. Because cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So the tangent has got, the graph of the tangent function has got vertical asymptotes everywhere that the cosine of the function is equal to 0. All right, let's take a look at basic just tangent function. And we'll do this here. So let's look at the tangent. We're going to do some basic transformations. So we're going to look at a vertical shift and a horizontal shift. Now let's see. B times x minus k. We don't generally worry about vertical shifts, but we'll play with it anyway. So what I've done is I've just thrown the tangent function up there. I am going to, we're just going to play with some of these transformations. So let's start out at 0. Okay, so here's my basic tangent function. This is the same thing that I graphed a minute ago. What's going to happen if I make k be something other than 0? Well, k is going to give me a horizontal shift. So if I make k be, I'll start off easy, just say 1. Exactly what you expect. Our center line shifts off of 0, or off of the y-axis. So this inflection point right here, this guy, that was at the point 0, 0, is now at the point 0, 1. What if I do vertical shifts? Same thing, right? This point here that was at 0, 0 is now at 0, 1. Okay. What I'm more interested in is my horizontal stretches. So let's see what happens if I make this be 2. Okay, you see what happened? When it was 1, my period is pi. So the period of the tangent function is pi. It's a little different than our others, so that's something you might want to remember. If I make this guy, this b, be 2, my period becomes pi over 2. So we can use the same reasoning that we used with the sine and cosine. We take our period of our undefined or our untransformed function and we can divide it by whatever our internal multiplier is. That gives us our new period. If I make my period be 1/2, I get if I make my internal multiplier be 1/2, I get a period of 2 pi. Again, not too surprising. All right, so let's put this guy back to 1. And let's look at vertical shifts. Now, vertical shifts are a little trickier because typically what we have to do, so let's look at an untransformed tangent function. You see there's no real good points that we can read, but we usually have to find one. So there's some things we know. We know that at pi over 4, the tangent is 1. Because at pi over 4, 45-degree angle, x and y are equal. Sine and cosine are the same. They're both square root 2 over 2. So tangent will be 1. So we can keep that point in mind. Okay, now, what happens if I make my vertical multiplier be 2? Well, where is pi over 4? Now I have a different point. I have pi over 4 for the x, and the y that is going with that is 2. So from there, I can get my vertical multiplier. So you can look for points that you know and read them off the graph, and from there you can get the vertical multipliers. Okay, so what to take away from this? Domain. Is theta cannot equal what? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So it's pi over 2 plus a pi. Right? Because at all of those places, cosine is 0, and k is any integer, positive or negative. The range, remember we zoomed all the way out and it never stopped? So the range is all real numbers or negative infinity to infinity. All right. While we're here, let's look at cotangent. Which is, we review that as cot, C-O-T. And that is, remember, whoops, sorry, the tangent theta, is 1 over the tangent of theta, or, sorry, cosine theta over sine theta, or x over y. So if we look at a graph of cotangent theta, it's going to look like tangent kind of flipped upside down, right? Actually, it kind of looks like tangent shifted. Let's put tangent on there and see and take a look at that. So tangent x. So let me make tangent dotted so that it is not quite so messy here. And let's take a look. So the blue dotted lines are my tangent function. The red line is cotangent function. And what happened? Well, it kind of looks like tangent shifted and turned upside down, but let me put another line here. If we look at mirroring tangent across this, no, that's not going to work. Never mind. So here's what you need to remember. Cotangent is 1 over tangent, which means that cotangent is undefined wherever sine is equal to 0. So for this one, it's undefined wherever sine of theta equals 0, which means our domain is theta cannot equal what? Pi, right? Multiples of pi, integer multiples of pi. So k pi. Your range, same as tangent, negative infinity over infinity. Period for both of these is pi. Right? You repeat every pi. All right. That's tangent and cotangent. I do have, let's take a look at an example from your text. Let's see. Let's take a look at this one. So this is in your text, and our task is to write the equation of this graph. And first thing we have to decide is what shape. Now this is Desmos, so I can zoom out. And we can see that it is tangent. Yes, so this is going to be a tangent. What else do we know? Well, we can see that we've got an inflection point. This point right here, where we go from kind of curving down, kind of curving up, this is called an inflection point. That'll mean more in calculus, second term calculus, maybe even. Yeah, somewhere in there. Anyway, so we know we don't have a horizontal or vertical shift, but we probably have stretches. In fact, we know we have a horizontal stretch, right? Because what is the period of this function? We've got a point at 0, 0, and we have a point at 8, 0, and nothing in between. So the period of this thing is 8. So what does that mean my multiplier needs to be? Well, let's take a look. Let's erase my scribble here. This way. Okay. So what do I know? I know I've got f of x equals a tangent times b x. I know that my period is going to be pi over that b. And I know that the period on my graph is 8. Yes. So that means b is pi over 8. Okay. Let's try that. Let's turn on this guy. These lines are my standard tangent function. Let's make my internal multiplier, my b. Let's set that to 8. Oops. What should that be? That should be pi over 8. There. Hey, I got my period right. But that means I've got a vertical stretch too. How do I figure that out? Well, it looks like the point 22 might be on my graph of my function, and it is. Where is that point on my standard tangent? Well, let's see. Let's just see what we got. So we know right now that my function is equal to 2 times the tangent of pi over 8 times x, or I should be using it. Let's make that an alpha. There we go. That's better. Okay? But I also know the point 22 is on my graph. So 2 is equal to 2 times the tangent of, no, that's not a 2, is it? Come here. I don't know that number yet. Head knows that number, but we don't know that number yet. Those are A's. Times pi over 8 multiplied by 2, because that is the x-coordinate of the point that I picked off my graph. Which means that 2 is equal to a times the tangent pi over 4. Tangent of pi over 4 is 1, which means that a equals 2. So let's check that. Let's make my multiplier here, b. 2. Hey, there we go. So the graph of the function, the function that describes this graph is f of x equals 2 tangent pi over 8. Oh, we'll make those be alphas, not x's. Alpha. There we go. That wasn't so bad, was it? Okay, you can do this. Let's talk about some, what's next? Cosecant. Cosecant theta. Cosecant theta is equal to cosecant theta is equal to 1 over sine theta, which means that, like cotangent, this is going to be undefined, where sine equals 0. So let's take a look at cosecant. This is going to work a lot like the tangent function. I'm going to, so I've got a sine function on here in blue just for reference. And let's watch what happens if my point goes around my circle. My cosecant function is going to appear. And you can see that it looks just like 1 over the sine function. So if I scroll out, again, we can see the vertical asymptotes. This is where sine equals 0. The period of cosecant is 2 pi. The domain of cosecant is going to be all angles except integer multiples of pi. So pi, 2 pi, 3 pi, 4 pi, negative 2 pi, negative 3 pi, yeah. Right? We can determine the transformations of cosecant in much the same way that we would determine the transformations of sine. And let's take a look at that real quick. So this is an example, again, from your textbook. It's example 2. And our task is to write the equation that would represent this function. But before we do that, let's take a look at, so this is cosecant, period 2 pi, range. Oh, what was the range on that? Cosecant. Well, let me take off my sign and it will become more obvious. What do you see? We see holes between 1 and negative 1. Yeah? So here's my range. My range is kind of interesting. It's everything except the numbers between 1 and negative 1. So it's negative infinity up to and including negative 1, union with 1 to infinity. What's the domain? We already said it. Domain is all theta not equal to k pi, where k is any integer. Now there's a related function, secant, and that is 1 over cosine of theta. Yeah? Now, this function is going to be undefined wherever cosine equals 0. This function will, it shouldn't be too surprising, have the same period as cosecant, which is 2 pi. Its range is also going to be the same, negative infinity up to and including negative 1 and 1 to infinity. And the domain is theta not equal to pi over 2 plus k pi, where k is any integer. Okay? So let's take a quick look at the graph of secant. Before we try that example. And this is kind of the same thing, I just zip through it. So, unit circle, I could let the point go around, but you guys got the point by now. We've got a cosine function in blue, and then we've got a secant function And it looks a lot like cosecant, except shifted. So there is actually an identity. That you should memorize and prove to yourselves. And it is that the secant of theta is equal to the negative cosecant of theta minus pi over 2. And there is a website actually that you should take a look at. Let's see if I can find it. Yes, mathwords.com, and take a look at the trigonometry section. And where are my trigonometry? The identities is what I want. Let's see if it's in here. Well, those are some of them. This is the page I wanted. So mathwords.com/t/trig identities. The reason I wanted to show this to you is because there's a lot of stuff on here, and I'm going to show you what you will want to know. So let me do this. The things that at this point in this class you need to know. Let's see. We will do. You need to know this identity right here. You need to know all of these definitions. You need to know this definition. These are all things you need to have memorized. Okay? You should know, you should memorize at least these two and be able to derive for yourself or memorize, whichever you choose, the rest of these. So blue means you need to have memorized. And by now you will have taken your first exam and realized the truth of what I'm saying. These you should memorize. The red ones means memorize. Or be able to derive quickly and easily for yourself. Okay, you should know this one and this one. From these two, you can get to all of the others. So these go under the be able to derive or memorize section. All right, so here's your sheet of things you need to be able to get to and the things that you absolutely need to memorize at this point in the class. Write this down. Make yourself some flashcards, some cheat sheets, but not cheat sheets that you can use on the test. These are cheat sheets to help you memorize. So you have the web page now. You know how to get here. mathwords.com/t/trig identities. Or you can click till you find it. You can find it in the trigonometry section. Okay. So let's go back to that example that we were going to start with a minute ago. This one. Our task is to write a function that will describe this graph. What are we going to do? Our choices are secant or cosecant. I like cosecant. No, I like secant, and here's why. I like secant because secant is 1 over cosine, and cosine goes through 1, 1. And so that means that this point that is currently at 2, 3 should be at 1, 1. Makes life easier. Sometimes it helps to think of these as the way that you would think of a cosine, but let's do it without doing that this time. So let's go back to my PowerPoint for a second so I can scribble. And since my computer is being so dicey, I'm just going to stay on this slide and risk it. Okay. So we've decided we're going to use a secant. And so we're probably going to have all of our transformations. So we're going to have A times the secant of B times X minus H plus K. Let's start with my midline. Where's the midline? Well, this thing bounces between -1 and 3. We would expect my secant function to bounce between -1 and 1. So I just put a red version of secant on here for us to work with. So in order to make my secant bounce between -1 and 3, 2 things have to happen. The first thing is I have to move my midline. And where's my midline going to move? It's going to move up 2. So that's just a vertical transformation of, 2. Let's not do my vertical transformation first. Let's before I do that, let's look at my period. So my period for this blue one is -2 to 6, which is 8. My period is 8, right? Okay, so we know some things. We know my period is going to be 8. We know my midline is what? 1. Aha, that's better. So it's a vertical transformation of 1. So my midline is my K. Let's see if I can't get to my horizontal shift. So my unadulterated secant function has got a y-intercept of 0, 0. My shifted secant function has got a midline at 2. So that means I need a -2 on the inside. All right. So right now I'm focusing on this one right here. We'll get the rest of these lined up when we adjust period. I'm getting there. So that means my H, my horizontal shift, is going to be 2. Now let's take a look at my period. So period is 8. My period on an adjusted function, a transformed function, is equal to 2 pi divided by B. Just a minute, let me shut my door. Sorry, I'm at home and my dogs are excited about something. Okay, we know my period is 8. So 8 is going to equal 2 pi over B. So what's B? B is going to be 2 pi over 8 or pi over 4. So let's write down what I've got so far. I've got f of x equals A, we'll figure A out in a minute, times secant of pi over 4 times, they're going to be alphas again, alpha minus 2 plus 1. Let's check that. I said that was pi over 4. Hey, that looks pretty good. Now, what's my vertical shift? Well, I'm almost there. If we think about my cosine, cosine bounces between -1 and 1, which means I've got an amplitude normally of 2. This guy has an amplitude of 4. So it's my multiplier. 2, right? Let's see. Sure enough. So when I figure my amplitude, if I go from peak to valley, my multiplier is half of that amplitude. Okay? So my function is described by the equation 2 secant pi over 4 times alpha minus 2 plus 1. All right. I am going to leave it to you. Should have done that. I'm going to leave it to you to prove to yourself that identity. The one that I gave you, which said that is on my little snippet. This guy. Cosecant. Oh, we'll do it. Cosecant pi over 2 minus x equals secant x. So let me erase my ink. Isn't that hard to do? We're going to prove that secant of any angle is equal to the cosecant of pi over 2 minus that angle. What we're going to do is we're going to start with secant. And we're going to remember that secant is equal to 1 over cosine. Now we're going to use our cosine to sine identity. This one, it says that the cosine of an angle is equal to the sine of pi over 2 minus that angle. So this is equal to 1 over the sine of pi over 2 minus theta. And just that easy. 1 over sine is cosecant. So we have just proven that the secant of theta is equal to the cosecant of pi over 2 minus theta. All right? Not that hard, correct? Done. All right, have a great day. We have some web conferences coming up soon, so check the Canvas site for when those are scheduled. If none of the scheduled times work for you, please get a hold of me by email and we will set up a time that does work for you. These are not required. These are optional conferences for your benefit to get your questions answered. So do feel free to contact me by email. I will talk to you all again soon.